Hi everyone, welcome to my YouTube channel, and I hope you guys had a wonderful weekend. This video will be the continuation of the last video where I've been talking about the gambler's ruin topic. My goal is that I can talk about martingale, stopping time. So there are many topics that I can talk about from gambler's ruin, and if you guys like it, I can definitely talk about martingale. I think martingale as a concept is very interesting, so that's for now. And let's look at this slide. So we will continue from the case when we had P and Q is equal to 1/2. So recall that we are dealing with the so if you guys don't know this gambler's ruin problem, like the setup, I encourage you to look at my previous video where I will be talking about some setup. Basically, we have two players, player A and B. They will be playing against each other. When player A wins, he or she will get $1 from player B. If player A loses the match, then he or she will give $1 to player B. And last video, I only talked about the case when, so this P is the probability of player A winning the match against player B. For that video, for the last video, I only talked about the case when P and Q are not equal to each other. But when P and Q are equal to each other, we do have to be a little bit more careful, because when we want to find the generalized form of solution for this, the probability of player A going bankrupt is a little bit tricky, because we have this multiplicity of root for our characteristic equation. So we do have to be a little bit more careful about that. So let's look at that problem. Our equation, so this one is, you get it basically by applying the law of total probability. And so this is what you get. And this is our equation. And remember that for solving this kind of difference equation, one method is we can do the iterative approach. Okay, I can definitely talk about this approach next time. But for this video, I will talk about the another approach, which is just basically you are guessing the form of the solution and find the constant number in front of that. So so let's look at the second approach. So we will be guessing that solution is of this form where we have an exponential m raised to the power of k. We will be substituting this into here. Then we will get something like 1/2 times m raised to the power of k plus 1 minus m to the power of k plus 1/2 times m to the power of k minus 1. And we can pull out m to the power of k minus 1. That will give us this times this m squared minus 2m plus 1 equals 0. So we can either have this part equal to 0 or this part equal to 0. But when m raised to the power of k minus 1 is equal to 0, then m must be 0, which is a trivial solution, so we don't want to consider that. That means we are looking at this part, and this is our characteristic equation. So what are the possible roots for this equation? Well, notice that we have a redundancy here, multiplicity here too. m1, m2, both of them are equal to 1. So that means our solution, one of the solution is 1. But we still need another solution, another independent solution from this guy. What do I mean by that? We need another independent solution from this form. That means we have to try a different form of this kind of equation. Meaning that first we try u underscore k to be of this form. Now we can try something like u underscore k is equal to k, something like this. And why does this work? Plug that in. Plug u underscore k equal to k into the equation here, and we get 0. This part becomes 0. So u of k equals k. This one actually works too. And then using this, our generals, then we'll get something like this form. So u underscore k equals a1 times 1. This 1 is from this guy. That's when we had m raised to the power of k. And then this a underscore 2 times k. This k is coming from this guy. So we have two independent solutions and we combine them. We did the linear combination of those two, and that is our general solution for this problem. And we are not done yet. We have to find both A1 and A2 using the boundary condition. So boundary condition for this problem is still the same. When we are at any point in the game, when the player A is having only 0 capital, that means that person will be bankrupt, and so that we have a guaranteed probability of 1. When the player A has a capital of A during any point in the game, that means that player will not go bankrupt. That means player B will go bankrupt. So using that, U of 0 equals 1 and U underscore A equals 0, you can find that A1 is equal to 1, A2 is equal to negative 1 over A. So when you substitute this two value into here, we get this, and you can simplify this. We get A minus K over K. That's for P and Q, they are equal to each other. Now I did this here. So for the case when P and Q are not equal to each other, we have U of K of this form. So these two are slightly different. Notice that phi is Q over P. So far we only have dealt with the probability for player A's perspective. You may be it is a legitimate questions to ask. How about for player B's perspective? You can either start this from scratch for player B's perspective, you will get the same answer, but we can be slightly more clever and notice that let V be the probability of player B going bankrupt. Then we must have U underscore K, that's for the probability of player A going bankrupt, and this is for the player B going bankrupt. Both of them have to add up to 1, right? And so you can solve for this V by setting this equal to 1 minus U of K, and you will get the probability of player B going bankrupt. So yeah, you don't have to do this from the scratch. So that's what I want to mention. So Gambler's Ruin for 2-player is well-developed problems. It is, I will talk as much as I can about all the bunch of variations in this problem. We also have a Gambler's Ruin for 3 players. This one is a bit difficult because you do need to know some martingale, and like solving this requires like using some results from Poisson kernel of the disk. I know this it's a bit difficult, but I can talk about this like when in the future videos. So for now, I will talk more about the Gambler's Ruin for 2 players. We will also talk about the finding the average time for this game, and then that will be using, I think, conditional expectation. So I will talk about the conditional expectation. And right, so let's look at some few more problems in this Gambler's Ruin problem. So problem 1. So far we only have dealt with like player A either wins or loses the match against player B. How about we include a third case when player A and player B can draw, right? I think this is very plausible case. So let's consider that possibility of draw, and we can denote those probability by P, Q, and R. So P is the probability of player A winning, Q is the probability of player B winning, and R is the probability that both of them have a draw. So we want to find the probability of eventual ruin for player A, so U of K. So how should we think about this? We would have to apply the law of total probability, and in this case we would have 3 cases. So U of K, we can so from one time step to the other to another one, we have either player A can accumulate 1 more capital, so we have K plus 1, or we can have a draw, so player A's capital does not change, or we can have a player A losing against player B, so that means player A's capital will be decreased by 1. So this is what we have, and then we can do the law of probability. So what do you think our U of K should be? So pause this video for a second. Try to come up with your own like the equation for u of k. So you should get something like this. And then the boundary conditions here, they are still the same. So u of 0 means like the probability of player A's going bankrupt when player A's capital is 0 at some point in the game, then you are already bankrupt. So the probability is 1. So you are guaranteed to be bankrupt. And so yeah, and we can rearrange this equation by putting this one, moving this u of k to the other side, and we get this form. Okay, so this may look intimidating, but notice that we have a 1 minus r. This is nothing more than p plus q, right? Because p plus q plus r, they must add up to 1. So 1 minus r is equal to p plus q, and we have this guy. And we will be doing the same thing. We will guess the solution to be of the form like m to the power of k. And you do that, you pull out m to the power of k minus 1. So we have a characteristic equation like here, and we can find the roots of this equation. So what are the roots? Well, when you do the when you factorize this equation, we get m1 is 1 and m2 is q over p. So the general solution is of the form a1 times 1 plus a2 times m2. m2 was this guy. But then we have a, remember we have a, is m to the power of k, so we have a k here, right? 1 to the power of k is just 1. So, and then we have to use the boundary condition to find the constant for a1 and a2. And when you do the calculation, you get something like this. And this is exactly the same as this one, right? So, so the only difference is that we have a, for here we have p plus q is not equal to 1. If you look at here, we have a, so for this one, p plus q is equal to 1, but here we do not have that case. So that's the only difference, but we still get the same expression. I find it very interesting. So for the next questions, next example, we have the case when the payout for the game is not either +1 or -1. If a player A wins, that player will get $2. If player A loses, then that player lose only $1. So that's the only difference in this example. I have not included the case when we have a draw. You can do that, but I think this problem is a little bit messy, so you will see why. We have a player A starts with K capital. Player B starts with A minus K capital. So this means that A is greater than K because player B cannot start with negative capital. And then the K can be any integer from 1 to A minus 2. I think this is the key. And if a player A has an A minus 1 capital during any point in the game, then player A can only get 1 unit, not 2, if A wins that match, right? Okay, and then we just assume that player A winning is given by this 1/3, and then the losing is given by 2/3. And we want to find the probability of ruin for player A. So we want to find the u of k for this problem. You can pause this video here and you can try to do this problem on your own. This one is a little bit difficult because yeah, you will see why. So I will move on to the next slide. So here we do not have a possibility of draw, but so that's at least good part. So one thing that you have to be careful about this problem is the domain of this function u of k. And what do I mean by this? So this one should be typo here, but so first of all, for k from 1 to a minus 2, the using the law of total probability, we get something like this. And notice that we have a k plus 2, not k plus 1. So that is the key part here. And then, so k equals to a minus 1 is not considered in this equation. Actually, that will be part of the boundary condition. So here, this problem we have 3 boundary conditions, not 2. So why do we need 3 boundary conditions? That's a good question. So when you look at this equation, what do you notice? The time step here, the step size is k plus 2 and k minus 1. So we have a difference of 3, right? K plus 2 minus this guy is 3. So we have a 3. So this one is actually this equation. We are dealing with a third order linear difference equation. And the boundary conditions are, so I talked about having 3 boundary conditions for this. 2 boundary conditions are still the same. Like u of 0 is still equal to 1, u of a is still equal to 0. However, we do have to consider another boundary case, and that's for when k is equal to a minus 1. When k is equal to a minus 1, is this part. You can only get $1 if you win. So this is what we have. So when you win, you have, so this is the probability of winning, and you will go to u of a. And then when you are losing, when you lose that match, when the player A has a minus 1 capital, then you will go to the a minus 2. So this part is still the same, but this one is slightly different here from here. So we have a 1 equation and 3 boundary conditions. 1, 2, and 3. So you do have to solve those so you have to solve for, you have to find the constant for those 3 numbers, a1, a2, and a3. Why is that? So when you look at the characteristic equation for this, we actually get a cubic equation. So we have, when you factor this out, we get this. That means we have here, just looking at this, we have a multiplicity of root, m1 and m2, they are equal to 1. And here we have m3 is equal to negative 2. Remember, we need 3 independent solutions, but so far we have 2, right? These 2 are dependent solution here. So that means we have to come up with another independent solution, and we will be using that, we will still try this one. U of k is equal to k. So this one works, and you get something like this. So this one, a1, we have a1 times this guy, 1 raised to the power of k. But 1 raised to the power of k is still 1, so we have a1 here by itself. We have a2 times k, and that is coming from this guy. And then we have a plus a3 times negative 2 here, raised to the power of k. Now we do have to find a1, a2, and a3. So that's why we have a 3 boundary boundary conditions. Otherwise, you cannot solve this equation. So we use that boundary conditions, and we get this equation. a1 plus a3 is equal to 1. Where does this come from? It came from here, right? You just set that you set k equal to 0. When you set k equal to 0, this one is 0, and this one is just 1. So we have a1 plus a3, and that is equal to 1. Now we do the same thing for this guy, and you get this. And for this guy, that's actually coming from here. Okay? So we have 1, 2, and 3 equations. So you can solve this equation. I already did that for you. So then you get something like this. a1 is equal to this guy. Yeah, you can find a3 on your own. a2 is given by this. And so when you combine all this, when you simplify this equation, you get something like this. I know it looks very complicated, right? Compared to, say, this one, we have, our expression is a bit uglier than what we have encountered so far. But anyway, I think that's for this video. For the next video, I will talk about the stopping time for gambler's ruin problem, and I will talk more about like a bunch of problems related to gambler's ruin problem. I hope that helps you guys solving this kind of problems when you are taking stochastic process classes. So I hope my video helps you guys understanding this probability. And if you are not even taking probability classes, I hope by watching my video on this, maybe that should be enough to give you some incentive to study probability on your own. So well, anyway, that is for this video. I hope my video helps you guys understanding this topic a little bit. And I will see you guys next time. And hope you guys had a great evening. And see you next time. Bye bye.